Good morning, everybody. Good morning. How was the weekend? Great. You did a lot of physics? Yeah? Yeah? Some of you are like, Today, finish up chapter 8, start review. Wednesday, review, which is going to be you coming with your questions, right? And then Thursday's the exam. Now, wait a second. Oh, I forgot to check this morning. Is this week the 9th week? Let's pull up the calendar. Yes. This is the 9th week of classes. Why is the 9th week of classes special? We're halfway done. Yeah. Try not to sound so excited.
If you only did one test.
So the 9th week of classes is also like the magic drop deadline, like you can still drop the class and get a W on your transcript kind of thing. After the 9th week, you can't drop. If you stop coming, you just get an F kind of thing. So there's a special drop deadline there. This usually sends people into a panic. So we're taking the exam on Thursday, right? And the drop deadline's on Friday. You are your own worst graders. So you might walk out of the exam just feeling ultra low, and you might go do something rash that you might regret. So what I'm going to try to do, I've done this in the past, I'm going to try to grade the exam as fast as humanly possible, which basically means I'm going to make some mistakes, and it's going to be kind of right-wrong. Like I'm just going to go through and like my first pass, right-wrong the exam, because I can do that one pretty quickly. It's the second pass that takes time. And then I'll post the grades for that. So I'm going to try and post those grades by Friday, right? So that will represent the lowest score you could possibly get on the exam, right? And I'll post the grades as if you do the exam autopsy. Does that make sense? So it's like a preview grade kind of idea, right? So that'll give you some idea about kind of how well. Do you guys want that, or right? Usually students want to know what their grades are right away, and I usually make you wait a week. But I don't want you to wait a week, have the deadline pass, and then say, Mr. Balogh, but you should have told me, blah, 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 right? So that Friday after the exam would be the day to contact me if you're worried about your grade in any way, shape, or form, right? You contact me, you come into GRASP, we go over it together, something, right? And I give you advice about how to move forward. So I'm going to do my very best. I should be able to get those grades definitely by Friday morning. But again, they'll come with qualifiers, and I'll make announcements about this on Canvas. It'll be sort of right, wrong, and as if you do the exam autopsy. You'll probably catch things that I'm going to miss, right? And truth be told, I probably won't do a second pass because I'll think I'll have graded it. And anyway, we'll find it all out in the exam autopsy. Sound all right? Okay. So that's the plan. That's the plan for this week. Let's do some physics, and then we're going to start reviewing for the exam. So this is another one of those problems where I didn't give you any numbers, just, be super annoying and be a physicist, right? This one's got springs in it. It's got friction in it. Like, how do I know it's got friction in it? There's a coefficient and there's a rough patch, right? Okay? So all of those things are sort of indicative of friction. Now, based on several questions I've got via email and in GRASP and on Thursday with the homework, there's a little bit of confusion, I guess, over springs and Hooke's law and potential energy. So before I do this problem, let's just quickly, because I didn't call it out in class because I thought reading would be enough. Hooke's law gives you the force that a spring exerts. And a spring exerts force based on how much it's stretched. And that's what that X is in that equation right there. Springs, we are not allowed to pick where the 0 point is for a spring. The 0 point for a spring is always its resting position. It's neither stretched, it's not compressed, it's just the natural position the spring would relax at. And so if we squish the spring up, then we'll get a compression, right? If we stretch the spring out, we'll get a stretch, right? And so that force, notice I wrote that without its minus sign. Those of you that went and looked it up in the book, and I grant you, this is confusing. Because a lot of places will write F equals negative kx, okay? And unfortunately, they're being lazy because what they really need to do is they need to put vector signs on the top of that force and that displacement. That minus sign right there, that is simply a reminder that if you stretch a spring out, let's say we stretch a spring to the right, which way is that spring exerting a force on your hand? It's to the left, isn't it? And if you push it to the left and compress it, which way is the force of the spring? It's to the right. So basically, what this says is whichever way you compress it, the force is, okay. So we handle directions of things in a free body diagram. And so that's why you'll see me and just about everybody else that kind of knows what they're doing, you'll see us not write the minus sign on there. It's not a literal minus sign. It's a minus sign to remind us of the directions that springs do stuff, but we handle directions with the free body diagrams. If you do a free body diagram, you put a spring in, you handle the direction there, and then you substitute the force as negative kx, you have now double corrected. It's like a negative of a negative, and then everything gets thrown off. So the practical advice for when you are working with springs is to ignore that minus sign. The magnitude of the force, the amount of force is equal to the spring constant times x. Spring constant is just something that tells you how stiff or floppy. Like slinkies are really low, jello's really low, car springs are really high spring constants. So that's Hooke's law, which tells you the force. But I talked about the potential energy that a spring has stored in it when it's compressed or stretched. Do you guys remember what potential energy equation was? It was 1/2 kx squared, wasn't it? And here, does it matter if we know that x is positive or negative? Yeah, whether the spring is compressed or stretched, why does it not matter? It's a square in there, right? You square negative things, they become positive anyway, right? And what are the units for potential energy? It's a joule, right? So this is measured in joules, this is measured in newtons, right? That's how you tell the difference, another way to tell the difference between those things. So Hooke's law, all about the force. Potential energy equation, all about the energy that gets stored in a spring. And the 0 point, I demonstrated this in class. The 0 point for a spring, we can't choose, right? It's set at the resting length of the spring. So I apologize if that was confusing for you, but I was hoping that the book would have been sufficient. I did find out how many people actually don't look at the book. That was interesting. All right. So what are we doing? We've got a mass sliding along a frictionless surface that has a rough patch in it, and then it comes into contact with some spring. So like here's my mass, and it's sliding along, right? It's got some speed v naught, okay? And then the rough patch here has a distance d with a coefficient mu. And then the spring constant is, all those things are given, and it compresses it distance x, right? So we want to find this x right there. That's our goal. We want to find out how far this spring is compressed. What do we do? I mean, like, first thing to do in visualization beyond drawing the picture is what? Do what? Oh, we need zeros. We need initials and finals, right? So initial here, right? It's, again, I know something. And then the final point will be where this spring, right, compresses its distance x. We'll call that the final point. This is the 0 for the spring right there. This would be like the distance x. 0 for gravitational potential energy. I mean, the lowest point in the problem is here, right? But does it change its height at any time in this problem? No. So don't need it, actually. Okay. So now that I have my initials, my finals, and my zeros, what do I do? The equation, the master equation, right? Work other plus energy initial equals energy final. All right. Let's tackle work other first. It's a Monday morning. We can do this. Is there any work that's not gravity and springs? Yeah, there's other forces in here, right? What's the other force? Friction. So if it's friction, I automatically know it's going to be minus the frictional force times the distance at x. How do I know it's minus? It's sliding friction, right? It's always x. The force, right, on this block is this way, but it's moving that way. Okay, so negative F times D. That was pretty good. All right. Initially, is it moving? Yeah. 1/2 mv naught squared, right? So if it's moving, it has kinetic energy. At that initial point, is the spring doing anything? Is the spring compressed or stretched when the block's at its initial point? Nope. No. And does it have any gravitational potential energy? No, right? So plus 0, this is my potential energy initial, right? All right. Just leave myself a little note that I thought about it. Okay, final point where that thing has come in and compressed the spring. Is it moving? Nope. Comes to a stop, right? Says it comes to a complete stop. Is the spring doing something there? Is it compressed or stretched? Yeah, it's compressed, right? So we're going to have a 1/2 kx squared. And then is gravitational potential energy any different? No, we're still at 0 for potential energy, gravity final. Okay, so there we go. Kind of flushed out everything here. Let's just rewrite to clean up. 1/2 mv naught squared equals 1/2 kx squared. That's what I'm working with. What are we looking for? Find the distance the spring compresses. What is that? That's x. Right? That's x. So it looks like I've got everything else. So just algebra now at this point, right? Well, okay. Well, yeah, we've got one more thing to do, don't we? What was it, Hisham? Did you say it? Yeah, well, we got to get rid of we got to do the frictional force, don't we? And friction is? Right? And so minus mu times n to, so now we've introduced the normal force. And in this particular case, what's the normal force? Yeah, it's just going to be mg, right? Because we're sitting flat on a surface. I mean, technically it's mg cosine theta, but theta is 0, right? So it's just mg. Rather than remembering it's mg cosine theta, I'd rather just quickly do a free body diagram. And remember, it's only mg cosine theta if there's only the normal force acting up. If you've got an additional force acting up for some reason, it's not mg cosine theta anymore. Do the free body diagram. Figure it out. Okay, so this is minus mu mg d plus 1/2 mv naught squared equals 1/2 kx squared. Okay, so now we've got to go solve for x. There's going to be a square root involved. I know that because it's squared. But let's see, can I multiply both sides by 2? So if I multiply that by 2 and that by 2, that cancels. And then I divide both sides by k. That cancels. And then I take a square root. That'll wipe out that square root right there. Oh boy, that was a lot. And then reverse it, because my math teachers always yelled at me if I didn't write it this way, which it doesn't matter. You can write it either way you want, because that's what an equal sign means. Square root of 2 over k times 1/2 mv naught squared minus mu mgd. All right, so my 7th grade, my 10th grade algebra teacher is yelling in my head, so I better clean this up. Let's see. Can I factor anything out here? I can factor out an m, right? 2m over k. What's that? I mean, I could, but then I would just end up putting a 2 on the other term, so it's a bit of a waste. V naught squared minus mu gd. I think that's like the most simplified form right there that would be decent for putting into a calculator. What's that? But yeah, this is, again, just me trying to satisfy somebody who's probably long dead. All right, so I tend to get things as simplified as I can because the fewer things I have to put into my calculator, the less mistakes I'm likely to make. That's how I roll. So, but now if I have the numbers, I go ahead and throw them in and see if my x makes any kind of sense, check it, see if it seems reasonable, that sort of thing. I remember a problem. Let me just show you what passed Mr. Balogh, the mistakes and sins that he committed, crimes against humanity. I gave a test question once. This was back when my exams, they were a different format. I think there was only 4 questions per exam, and each question had like multiple parts, and it was. This might even, you know what? I think this was when I gave open note exams, which, trust me, you don't want. You just don't want, and you'll see why you don't want it in a second. The problem consisted, it's like seared into my brain. There was a hill, and there was a mass on the hill, and yeah, there was a rough patch. I'm trying to remember if the rough patch was on the hill. I don't think it was on the hill. I think it was down here. There was like a rough patch. And then, and everything was frictionless unless it was a rough patch, right? And then there was another hill that was more like a launch ramp. And then there was another rough patch. And then there was a spring. I think, if I remember right, that semester the students picked camel for their object going down a hill in chapter 5, I think. And so a camel was sliding down I think the camel was sliding down a snowbank for some reason. I don't know what camel was doing near any snow, but a camel was sliding down a snowbank, and it hit a rough patch, icy hill, hit a rough patch, launched off of a snowboarder's like mogul, like trick jump, flew through the air, landed, went over another rough patch, and then hit a snowbank that acted like a spring. It was something like that. Yeah, okay, it was a bad day for the camel. And I think students had to find what the spring constant was for the snowbank, given how far, right? And so this had a coefficient that was different than this coefficient. This had a distance that was different than this distance. This had a height different from, I didn't give them the height over here. I gave them the angle and the distance down the slope that it went. There was a group of students outside my office door after that exam with like pitchforks and buckets of molten tar and torches They were ready to haul me out, draw and quarter me out in the town square. Like they were mad. They were just mad. What was the mistake? Why were they so mad? Does this look really hard? Yeah, it does, doesn't it? But it's actually really easy. Where do you put the initial point? Right here. Okay. Where do you put the final point? Over here. And then, what are the only things that matter? The rough patches. That's it. What happens in this middle part? There's no friction here. There's no air resistance. What happens to the energy here? You lose kinetic energy into potential energy, but then you gain exactly that amount. There's nothing lost here. Camel could have done a loop-de-loop, right? What my students ended up doing is they ended up like breaking it up into multiple parts, right? They found the speed here, and then added the speed here, and then some of them did like a chapter 4 projectile motion problem. And then they did, right? And then when I just came up and went, well, look, this is just minus mu minus F1 D1 plus a minus F2 D2 plus mgh equals 1/2 kx squared. They were very sad. Because what's this? Which potential, where? There's the initial energy, right? Okay. And then what's this? This is the final compression of the spring. Now, granted, I was mean in that you have to use like a d naught sine theta to get the height here, right? This height never enters into anything. Yeah. Do you hate that when you get information that you don't need? Right? Well, that's how the world works. Get data all the time that's like, did I need this information? Well, actually, no. So anyway, yeah, it can be bad. Like I said, I try not to make mistakes like that anymore. I still make plenty of mistakes. Last week, you guys didn't see it because it was my 4B class. I was 30 minutes into their lab explaining how to use a digital multimeter when I said, okay, now open your labs to this page, and they all looked at me like, what labs, Mr. Balogh? I'd forgotten to print out their lab packets for that unit. That was a mistake, right? That was a mistake. Okay, let's start review. Now, okay, so choose your own adventure thing here. Because you're expecting review to be on Wednesday, right? I'm not going to expect you to ask too many questions. But if you have questions, I want to answer them. We could do that. Or we can sort of go back and try to start remembering the chapter 5 and 6 stuff, right? Like we could go. So what is it you want to do? Do you want to concentrate on like maybe chapter 8 homework and getting that all finished up? And then do some more of the chapter 5 and 6 review on Wednesday? Or do you want to do like chapter 5 and 6 stuff today and do homework questions on Wednesday? 5 and 6 today? Okay, so let's do 5 and 6 today. And let's do this in the sense of like a, maybe like trying to develop a cheat sheet. Like why we put on a cheat sheet. Now in doing this, I kind of hesitate to do this just a little bit because part of the problem is that the way I would do a cheat sheet might be very different from the way you would do a cheat sheet, right? And so please make sure that you don't just make mine, right? Organize the cheat sheet to work for you. And I don't know what that looks like. Some people need boxes. Some people need to do it on the thing, whatever, right? Okay. So let's just take a look at the exam 2 topics, because we're going to use this to sort of, I know it's kind of small. I don't think I can zoom in on this screen. So let's see here. Yeah. Let's do this. Let's take that and just put it in here. I don't want all the text, but oh well. No, stop copying stuff. I just want to paste. Paste. There we go. Get this a little bit blown up here. And it's tilted, but I don't care. Okay, so here we go. Second law, second law, second law. Those are all chapter, let's see. No friction would be 5. With friction would be 6. Vertical circle would be 6, wouldn't it? Conservation of energy. 8, 8, 8, and 7. Free body diagrams, 5 and 6. Newton's laws, 5 and 6. Power, where was that? 7, wasn't it? We talked about the dot product in 7, and the work done by a force would have been 7. So just kind of getting the getting ourselves oriented with chapters, like kind of where stuff is, and just again, it's really 5 and 6 as they're really a combined idea, aren't they? It's all Newton's laws, and then conservation of energy is 7 and 8. So I really feel like there's just kind of 2 units on this exam. So how'd I do with number of questions here? There's 1, 2, 3, 4, 5. 1, 2, 3, 4. From 5 and 6, which means that there's 1, 2, 3, 4, 5. Oh, I can't count. 6. Okay, yeah. It's about an even split. It's about 6 and 6 for each of those 2 grand ideas, right? So, all right. So you want to kind of do that analysis whenever you're given something from a teacher that says, like, this is what's coming, these are the topics, all that kind of stuff. Try to orient it in where it fits in the course and that kind of stuff. Okay. So what are we going to do about remembering all this stuff from chapter 5, right? Let's jump into like problem solving first, and we'll come back to concepts in a second, right? Because these are the first things that kind of show up on this list. Second law, connected objects, no friction. Second law, so Newton's second law, connected objects, no friction. Where have you done that in this class? So there's something, there's like, with connected objects, right? You always have some sort, 2 objects that are connected over a pulley, right? And so it can be something like that. Let's see, did we do problem like, that was a homework problem that was like that. We did several in class that were like this, right? And then you did a lab that had this one, and that one, and that one. Notice here I'm just sort of quickly sketching out things that I've seen in the class, things that I'm trying to remember. You can go into the homework, right, and see all the sort of different, wasn't there a homework problem that had like, was it like a string and another string and something was hanging down? Yeah. Okay? Those are all examples of that, right? So what are the kind of things that you might want to put on a cheat sheet to help with this? So a cheat sheet, yeah, you can put, like, I would definitely have like the problem solving method down, right? But really how you go about solving things is a skill that you're trying to develop. And what you need on the cheat sheet are little reminders about how to do that, right? And so I'm guessing that you still feel shaky on like drawing a free body diagram and remembering like identifying forces and things like that. These are skills that with usage become more and more clean, but right now you might still be kind of like, oh, what do I do? So like pick something, right? Pick one of these, right? Maybe, I don't know, pick this one, right? And like go into your notes, go into your homework, and just get a free body diagram down. Now, are you going to have exactly this problem on the exam? Probably not, right? But something that reminds you about what to look for. You don't want to carbon copy this, right? What you want it to do is to jog memory, right? And so maybe you have this picture, right? And then don't forget like a coordinate system or something like that, right? And then like notes to yourself. Check directions of stuff, right? And what sort of stuff should you be looking at the directions of? Forces, the acceleration, which way gravity's pointing, hint, it always points down. Directions for your acceleration. You've made enough mistakes now that you should be able to go, oh gosh, I always I struggle with that hanging mat, right? Like I never know which way to make something positive, right? So try to condense that struggle that you're having with that one key area, right, down to a set of instructions that can help you remember what to do and at the very least have a 50-50 chance of getting it right. Now, ideally, you want 100%, right? You want to be able to say, oh, okay, well, if this thing is accelerating this way, that's the way I'm going to, right? But what are the possibilities of things that Mr. Balogh could ask about this, right? Well, what if it was accelerating the other way? And this might not be something you put on a cheat sheet. This might be something that you just do on scratch paper to the side, right? Just a real quick, like, okay, so what happens if I have a situation like, okay, I've got my thing, right? And Mr. Balogh says that the acceleration is this way. Well, what would that mean for the acceleration of the hanging mass? It's going up, right? If I don't give you the acceleration, then you can pick whichever acceleration you want, and your answer might come out negative compared to mine. That's okay. We're just arguing over which way is positive. So, you know, so you had probably was a penguin, and there was like an extra force, wasn't there? Okay. So what if Mr. Balogh says that there's another force like pulling up that way? Well, that's an additional force to the normal force, isn't it? So you've got to remember, you know, like, how do I deal with a force like that? Well, where would that force go? Like in the subsequent writing down of stuff.
Along your y-axis.
It's along a y-axis. It's like another force that goes into the y-axis, right? So what you need to have in front of you isn't so much like a thing to copy from. You're not copy-paste from your cheat sheet onto the exam. You want enough information to jog your memory, to help with your skill, right, in problem solving. I've been giving something. I try not to give you anything you haven't seen before, and some of you might argue for what you've seen before, but like, how do I handle this situation? Okay, so you're going to have like maybe a picture, and then you're going to have some notes to yourself, right? And it could be things like, check this, right? And like make sure I know what directions they are. And then Mr. Balogh always said to write down MA equals, right? And you can even sort of lay out the template, right? Where that goes to 0, right? And oops. So, do things like that. We got to have it for multiple objects, right? AX, M1, M1, right? And either have like the full setup from that particular problem. But again, remember that you've got to be flexible in your thinking as you're applying it to whatever situation I'm going to give you, right? But you want something down that's going to be able to jog your memory, right? Newton's second law problems are always about process. They aren't about what the final equation is, right? We develop the equation for every situation by applying Newton's second law in this method of drawing a free body diagram, asking the question, what's pushing or pulling on this object, right? So on and so forth. You guys know that these problems are kind of in-depth and lengthy, right? Like how long did Newton's second law problems take you doing the homework? Half an hour, 25 minutes, 4 hours? The average was 57 minutes, I think, or something like that. It was in the high 50s, looking at some of the homework problems, right? Now, that average can be thrown off because I think it only calculates the time like that the browser window is like open, as opposed to, computer's not sitting there staring at you, tracking time on task or any of that kind of stuff. Well, it is sitting staring at you, but that's that's Facebook, okay? So, but yeah, I know that these are kind of lengthy problems. How much time do you have on the exam to do it? About 10 minutes, right? Because it's about 10 minutes per problem. Did I tell you this already? I've sort of, the way I have written the problems and the information I've given you, I've tried to make the algebra easier. I can do that by like giving you unknown things, right? And it just makes I can kind of shortcut the algebra based on the stuff that I've given you. So do I think that the Newton's second law problem without friction and connected objects is doable in 10 minutes? No, it's probably more like 12 to 15, but I've tried to save you time on other problems. What's another problem that we could be saving time on, maybe? Concept questions, right? Good place for saving time, hopefully, right? Hopefully you can just kind of fire those off, right? Power. Like, how hard is it to calculate power? Take the work divided by the time, right? Take force and multiply by velocity. Like, convert from horsepower, like, compared to Newton's second law, that's not very hard, right? So hopefully that's one that you can just do. No, I'll give you a conversion factor. Any conversion factor you want, I'll give you. So vector dot product. That's going to be a straight up math problem, right? I would hope that you can get that one done in less than 10 minutes. Just two vectors dot product, boom. Right? It's either going to be a times b times cosine theta, or it's going to be ax bx plus ay by, right? Whatever form of the dot product you want to use, get it done. Work done by a force. That's like force times distance. Get the right component, right? Get the component of the force that's going in the same direction as the displacement. So I've tried to give you problems, right, that are a little bit quicker and faster. And then there are some time sinks on there, right? So what does that suggest about the ones that you want to do first? The first problem on your version of the exam is a second law problem. What are you going to do? Right? Okay. Right? Unless you just feel super confident, like you could be different from the average, right? It could be that you struggle with conservation of energy, but Newton's laws is your game. Great, yay, right? Do those. So every brain is different. Every person's skill in various areas is different. You really have to tune this to you, right? But also, remember, I made it easier for you to identify what the problems are about, right? Because it'll say right on there, topic, right? It's question text, and then at the end of the text in italics, it gives you the topic, okay? So you hopefully be able to manage your time on the exam. Is any of this helping you? How many of you are feeling more anxious now that I've started talking? Okay, right? It can happen, right? But do you know what to do? Do you have some actionable things to do? Okay, right. So it's anxiety, but it's like I can do something about it, right? It's not the existential doom of I'm dead. That's there too? Oh, it's help. This helps? Okay. Right, so yeah. All right, so second law, connected objects with, and I mean, maybe I finished this, maybe I didn't, on my cheat sheet. So like, this is like my prototype cheat sheet, right? I'm just trying to get ideas down. I'm trying to bring things together. And then I'll probably make another one that's got like the actual like clean, my cheat sheets in college, I had to write very slowly for me because my handwriting is so bad. And so I had to like really try to make my cheat sheet a work of art. You guys, some of you have just amazing handwriting and ability to draw stuff. And it just blows my mind how good you are. So, but make the cheat sheet useful for you, whatever that means, right? Big writing, small writing, on your computer, print it out in miniature font, whatever. But getting tons of examples on there may or may not be the best way, right? Because if you've got tons of examples on there, it's a little bit like an open book exam. Do you guys know what happened in the open book exams when I gave them? They failed. Yeah, why did they fail? Because they didn't study, right? They're like, oh, I'm going to have the book. I'm going to have my notes. Well, they sat down for a 2-hour exam. Do you have time to study and learn some stuff while you're trying to figure out no, you just don't, right? And there was death. There was blood on the walls. It was bad, right? It was horrible. I'll never make that mistake again. Okay, second law, connected objects with friction. I told you I'd never make that mistake again. The pandemic forced us into that. Because students had to take them at home and there was no way for us to, I mean, we could have used all that invasive stuff. What was that called, that program that they make you test with? What is it?
One of the programs I've used was ProctorU.
ProctorU, where like you have to do the camera and you have to scan the room. Oh my gosh, it was terrible. Yeah, so we just let them do open book, open note, and we gave them a 20-minute time limit for 2 questions per week. It was oh my gosh, it was so bad. It was so bad. What are we doing? Second law, connected objects with friction. That's telling that I'd rather think about the pandemic than second law, connected objects with friction. Okay. So it's kind of like this, right? But with friction, what do? Yeah, there's some force resisting the move, and we have to know what the move, like, if it's kinetic friction, you have to be told something about the movement, right? Or if you know, for example, that on this one that I drew right over here, okay? See how I drew that extra purple force up the slope? What do you now, if that's kinetic friction, what do you now know about the direction it's moving? It's sliding down the slope, isn't it? And it's pulling this one up. Now, does that mean that's the direction of the acceleration? Not necessarily, but you could just say acceleration's this way, and if you guess that wrong, your answer will simply come out negative compared to, right? So anyway, you don't need to worry so much about that. But again, just having, now, are these two very different from each other? I mean, when you introduce friction, you have to remember fun. And so like mathematically, it does get a lot harder, doesn't it? Because now the y direction, you got to find the normal force. And with second law connected objects, no friction, the normal force doesn't enter into the situation if it's on a slope kind of thing. So like, you know that second law with friction is going to be a doozy, right? So I don't know, either save it for the last or do it very first quickly.
With the problem with static friction, how do you like, when doing the problem, how do you find the max static friction and the regular static friction? Or is it the same thing?
No, static friction is so bad. All of you that have asked me the same question hate the answer because the answer is it depends. What's the one thing you know static friction is doing?
Pushing away from the force.
Keeping the two surfaces from doing what? Moving relative to each other, right? So there's a really good chance that if static friction is involved, the acceleration of that object is 0. But again, it depends. Because if you have like a cardboard box on a flatbed truck, and the truck is accelerating forwards, and the box has static friction between the bed of the truck and the box, does the box have acceleration? Yes, right? And what's the force that's doing the accelerating? Static friction. Because if it wasn't, the box would be sliding off, right? The look on some of your faces is like, oh my gosh, I'm dead. I'm dead. I didn't understand a word of what just happened. So here's my Kleenex box and here's my stapler, right? Okay. If I accelerate it, take it from 0 speed here to some speed here, what force accelerated the stapler? It has to be horizontal because the acceleration was horizontal, right? So what's the only force acting in the horizontal on that stapler? The box, right? And that force was the force of static friction between the box and the stapler. Was it my hand? No, because my hand is not in contact with the stapler, right? Box is in contact with the stapler. So there's an example of static friction accelerating an object, right? So it can happen. Now, because it's second law connected objects with friction, could the connected objects be not moving and you have static friction? Sure. I don't think I did that to you. I'm pretty sure it's kinetic friction. So I should probably go and look, but I'm not going to.
There was a homework problem where it was like 2 blocks on top of each other.
Yeah.
And it was like, what would be the force in each of one block?
Yeah. You got lost on that one, right? It's important to understand the concepts behind all your homework problems, right? The concept there is Newton's third law, 2 objects interacting, pushing or pulling on each other, right? Was it like block C sits above block A or whatever, right? Okay, and then you lift it off and it starts sliding or something like that. When those 2 blocks are together, as far as the table's concerned, does it know about this block up here? No, but it does feel the weight of both blocks, doesn't it? So why would it start sliding if you move that block, if you take that block up? We've reduced the normal force, right? We reduced the weight that's pushing down on the surface of the table, and we know that friction and fun go together. If the normal force goes down, the friction goes down, so now it starts accelerating, right? So there's the idea behind that. How do you put that kind of stuff down on a cheat sheet? I mean, you could, but words suck. And math sucks more. Pictures are cool. As a person that cannot do all 3 of those things very well, right? I'm in the wrong job. No. A lot of this is about practicing it. You need to rely on what's in your head. Learn it, right? Okay? Learning it, getting into your head. The cheat sheet is not your brain. It's a safety blanket. It's a reminder for when you have that anxiety and you're freaking out and you can't quite remember. Which way does the normal force go? What component do I need? Right? It's that thing you can turn to jog your memory that is there, right? Tomorrow, Thursday, you're going to be running this race, right? You're in the marathon and you've got to do it, right? I can't run it for you now. You've got to do it on your own. But you want to have cheat sheets at every mile or so going, you can do it, it's okay, remember this thing, right? That's what your cheat sheet is. A cheat sheet doesn't run for you, right? It's this encouragement, it's this reminder, it's this jogging of those brain cells and refiring those synapses. And you can't form those synapses if you haven't been doing it, right? Which is why I've been preaching the gospel of do physics every day, right? As much as you can, because you need to learn, got to get your muscles built up. Okay, where are we at? Second law, vertical circle. Oh my gosh. So that one is different, isn't it? Circle, we concentrated really on 2 points in that circle, didn't we? So really we can go like normal, mg. And what way is the acceleration here? It's towards the center, so it would be up, right? And then normal and mg and acceleration down. So maybe have the Newton's second laws for these written out. Like there aren't that many variations. What's the only kind of other variation you saw? It was like the vertical circle, but something was on the outside, wasn't it? Okay. Where we have mg and the normal force pointing up like that, right? There's like cars going over a circular hill or something like that. I think there's a homework problem about that. Somebody said sideways. What happens, like what direction is the tension here? I don't know what's holding this thing in place. But if this were like a roller coaster, what force is pushing? How do you know there's a net force towards the middle? It's going in a circle, right? Circle by definition means there's acceleration. In what direction does the acceleration point? Towards the center. So that means there has to be a force towards the center, right? So if that were a roller coaster, what would that force be? Be a normal force. If it were a tennis ball on a string, what would the force be? Tension in the string, right? It's got to be something that's pushing or pulling that object into that circle. So just having, again, do a total rough draft, do a core dump, do a brain dump, right? When you look at this and you go second law, connected object, vertical circle. What was, look in your notes, right? Flip through the homework. I hate penguins, right? And then just kind of barf it onto the page. And then when you've got it barfed onto the page, start, cleaning it up, condensing it, summarizing what are the key things that I need to help me remember how to do this. Again, that's why it looks different for everybody. So that was second law vertical. Is any of this helping you? Okay. So that gets us 5, 6. Okay, now we're to the free body diagrams conceptual and Newton laws conceptual. Okay. One game you can play is, how could Mr. Balogh possibly ask me a question about free body diagrams conceptual? Like, what would a conceptual question about a free body diagram be? So it could be, draw a free body diagram of this thing, right? I give you a situation, you draw the free body diagram. And that's all I ask you to do. I'm not asking you to solve anything. I'm not asking you to play. That's definitely one way I could do it. In general, though, you know that I give you conceptual questions that are like multiple guess, right? That give you some things, right? So could I give you a free body diagram and label the forces and you tell me which force is incorrect? Or could I give you a situation and then like 4 free body diagrams and I say which of the following free body diagrams is correct for this situation? So what is the skill? What am I asking you to demonstrate in all of those examples? Identifying and labeling forces, right? So what does a cheat sheet look like for like conceptual questions? I don't know. I struggled with this too. Having free body diagrams of things. For me, it wasn't so much having diagrams of all the possibilities, because they're kind of endless, aren't they? Like, what's the free body diagram of a rocket taking a bird, or like, But the process. What is the process? What question did I just repeat over and over again you should be asking yourself when it comes to a free body diagram? What are the pushes and pulls, right? And if you've got a force, what do you have to make sure you can also identify? The object that's creating it, right? That's an application of Newton's third law. Forces exist because 2 objects are interacting with each other. So for me, my brain, my personal universe, I needed a list, right? Free body diagrams. Now, this speaks volumes to how kind of nerdy I am. So I am a hobbyist pilot. I don't fly real planes, I fly simulated ones. But I treat my training as if I were training for my pilot's license. And so I study procedures. One of the things that pilots do all the time, well, good pilots, the ones that are still alive, checklists. Standard operating procedures. When I was in graduate school and we were working with uranium, we had standard operating procedures, things that you always did when you were handling uranium. You always did this, you always put your gloves on, you always put your mask on, you didn't open the, right? And we had the list right in front of us. In emergency wilderness rescue, which I did do, we again had standard operating procedures. We got to go over a cliff to rescue somebody. We're going to make sure this, we're going to make sure that, we're going to get this click, we're going to have somebody else check it, right? There's these standard operating procedures that keep you safe. So what's the standard operating procedure for a free body diagram, right? It's a third law, right? 2 objects, name object for force, and I've got to go back and write that out real clearly, right? Okay, so then like label all forces, right? And then, what was it? Coordinate system, right? So like, and you can go back to the lectures on YouTube, you can go back to the PDFs, you can go back to your own notes. Figure out the process and be able to apply the process, right? Instead of, it's like, trying to write down every single possibility here would fill up, well, there's thousands of physics textbooks out there, right? Process.
In a free body diagram for like a bird flying through the air, the force that's acting upward would be between the bird flapping its wings. So like
Yeah, it's lift, it's the wing force, the levitation force, the magic force. But you know there's got to be an upwards force. Why do you know there has to be an upwards force?
because the bird would be falling into
Otherwise, the bird would be in free fall, right? So it's kind of like a normal force, but is it contacting anything? Well, no. So maybe we'll call it the wing, right? To contact with the air. Now, is there air drag? Sure, right? And then if this bird is flying at constant speed, there needs to be some other wing, rocket, motor, however birds do it, right? But I know that I've got to have balanced forces. If it's not accelerating, the forces have to be balanced. How do we know? Newton's second law, right? If the acceleration is 0, the sum of forces has to be 0. So now we're getting into concepts of Newton's laws, conceptual. Was there a hand back there? Yeah.
You know, sometimes the normal force is equal to
Mm-hmm.
energy, and sometimes
It depends. If the bird were flying upwards, if the bird were accelerating upwards, vertically upwards, okay, what has to change in this diagram? This one has to be bigger because I want my acceleration to be in that direction, don't I? So a free body diagram doesn't tell you which way it's moving, tells you which way it's accelerating. And this is an application, like in a free body diagram, you're applying Newton's third law, identify the objects that are creating it, and Newton's second law. Remember, second law is about a single object. Third law is about two objects. And it can get confusing, but you're applying both of those at the same time. When do you apply the first law? We kind of mentioned it and then kind of don't really deal with it anymore, right? Because it really, the first law is just more about inertia. Tries to define what mass is, sort of. So it's not as big a deal. But second law and third law certainly are, right? So what are the conceptual questions I could ask you about Newton's laws? The free body diagram, I know you're getting a conceptual question on a free body diagram, right? But you're getting two questions. Two questions conceptual about Newton's laws. What couldn't I ask? Like, seriously. The whole universe is, like, how do you get all of that down on a cheat sheet? You don't. Again, you fall back to definition and process, right? For Newton's third law, it was important that we had how many objects? Two. That the forces were equal and opposite. So how do you apply that? We sang a song. Right? We sang songs. So could I ask you conceptual questions like about the song? We'd have to like think about the forces acting on a couple of objects and determine what's the same and what's different? Sure. How do I ask you conceptual questions about Newton's second law? Like, if a runner starts running, okay, what do you know about the force of the ground on the runner compared to the air drag? No, they're not equal and opposite. How do you know that the force of the runner on the runner from the ground, pushing the runner which way? Forwards, is bigger than the air resistance pushing backwards? Because the runner is doing what? Accelerating, changing their motion forward, right? We know that there has to be an unbalanced force, right? That's Newton's second law. Because how many objects have we talked about? Just one. Just one. We talked about the runner, right? The forces on the runner. Now, what can you tell me about the normal force on the runner and the weight of the runner? Okay, which way is the normal force? It's upward because of the ground. Which way is the weight? Down. Okay. What can you tell me about those forces? Those are balanced. How do you know?
The runner's not levitating in the sky.
We're not accelerating up or down. What have we talked about now? What can you tell me about the normal force on the runner and the force on the ground? They're equal and opposite. How do you know that? Newton's third law, right? How many objects have we now talked about? Two. The ground and the, right? Now, the runner turns into a basketball player and tries to do like a three-point shot. What can you tell me about the normal force on the basketball player as they come up off the floor? Compared to the weight. It's greater than the weight. How many objects are we talking about? Just one. The weight of the player and the normal force on the player, right? And how is that why is that normal force bigger? Because we're accelerating upwards, right? It seems like we're kind of splitting hairs, right? If you're sitting here now going, I don't understand. I don't see where there's one, where there's only two, that kind of stuff, right? Then study that, right? Get into it. Find videos online. Ask ChatGPT to quiz you. Go to the tutorial center. Email me. Do something, right? Mr. Balogh, what do I do to try to figure out? Read the book. This is amazing. I'll do anything except read the book, Mr. Balogh. Where were we? So yeah, preparing for these conceptual questions, I honestly, like the homework conceptual questions I've given you are the best bet. I know a lot of times, just based on the average time it takes you to get them correct, you guys aren't trying to answer them. Well, you're trying to get green boxes, as opposed to like really digging in and trying to answer what's going on, right? So you can't let that kind of thing go. We've got about 5 minutes left for class. Okay, so yeah, like what do I do for putting down equations on my cheat sheet, right, Mr. Balogh? Like, you haven't told me any, like, what do I put on my cheat sheet? Like that, I mean, that's it, right? That's the toolbox for chapters 5 and 6. But you know that that's a lie. It's the truth, but it's also a lie. It's the truth because that's really all the equations that we are given. All the other math comes from that, right? Is a product of applying those equations, which is the part you guys don't want to do because that's the hard part. You got to learn, right, to apply those things. But that's what we're asking you to do. Now, I mean, can you write down things like that? That depends, right? That equation only works if there's only weight down and a contact force on a hill, right? But what if you're given a different situation? Like, things like these they're traps, okay? They're not broad results like the same way that projectile motion was. Projectile motion, we had our 3 equations in the box, right? And it was just a matter of figuring out what inputs to put in. Here, you're making the toolbox as you go. The Swiss Army knife is F equals MA. What tool do you need for that? Those 2 awful words. It depends.
For chapter 7 and 8, is there only the...
In chapter 7 and 8? It's a little bit better. I mean, there's a little bit more. Work other plus energy initial equals energy final, where kinetic energy is 1/2 mv squared. Potential energy can be mgh, or potential energy for a spring can be 1/2 kx squared. There's work, F dot D equals FD cosine theta. There's power, which is work or energy divided by time. And then there's Hooke's law. Did I get them all?
I guess you could write the integrated version.
Nah, no, don't worry about that. I pretty sure that's it. But again, that's a little bit, it's hiding a lot, isn't it? Knowing where 0 is, knowing to do initial and final, right? Go through, do that same brain dump onto a page about the 7 and 8 material. And then start trying to formulate what you might put down on a cheat sheet. You don't want to be doing that Wednesday night. You don't have time for that Wednesday night. Oh, and do your homework. Oh, and eat breakfast and lunch and get a haircut and a job or what, like, it's a lot, isn't it? It's a lot. But you can do it. You can do it. I'll see you on Wednesday.